All right, so I went a little bit nuts on that. On that last on track two there, but because I went ahead and did all of this stuff, but we're never going to put you on an incline like this. We're just going to keep it nice and straight. All right, so and the net force of this is going down. But anyways, so the static frictional force until bang, then it becomes kinetic frictional force. Okay, kinetic is always a little bit less. All right, so friction characteristics. It's always less than the max. It's less than the maximum value of the static frictional force. They're independent of how fast things are going. Okay, they're independent of velocity, and they're independent of contact area. The contact, because there are so many, and this is strange. A lot of people don't realize this, but and I think we talked about this before when we were looking at some of the friction things. When we looked at friction earlier, the contact area makes no difference whatsoever, because the contact points where things are actually touching are so minutely small and spread out. You don't think it, but it is. But it is. If you could look at it with an electron microscope, you would see that even if you have like two heavy cubes of silicon, that 225 right next to each other, they are barely touching, of that mass ball that we saw, they'd barely be touching at any place. So it's regardless of the contact area. All right, friction, kinetic friction, other examples. Moving along. All right, so now we get to drag. All right, this is where we get to drag and pushing things through, and this is where we got the Magnus force and all that kind of stuff. Now, I cut out the Magnus force thing earlier, but what we are going to look at is the Felix Baumgartner video. All right, so what I want you to do is I want you to look at the Felix Baumgartner video, because drag has two components. There's viscous or skin drag. This is a friction between a solid and liquid surfaces, similar to, now we consider air like a liquid when we're doing these things. There's also pressure drag. The pressure at the front is greater than the pressure at the back of a moving object. And remember, force is equal to pressure times area, which we'll talk about the pressure. It was a crapshoot which one we were going to show first. Okay. All right, so here you go. Drag race formula. Here's the drag race formula. Yes, this works. Where this rho is the density of the fluid or air at the surface of the Earth. Okay, and the density of the air at the surface of the Earth, we're going to say is 1.2. And this is, we've done this before. And then notice, this is the velocity. There's nothing spinning here. And this is kind of the drag formula that we're going to use. What changes this coefficient of drag? All right, v is the speed of the object relative to the fluid. Okay, v is the speed. CD is known as the drag coefficient, and is a number that depends upon many factors, including the shape of the object. A is the front end cross-sectional area of the object. Okay. All right. So when you watch the Felix, and so when we look at skydivers, so we got these bicyclist things. I think I asked you a question. What happens to this force of drag if you double the speed? If you're not used to that, what happens to the force of drag if you double the speed? Well, let's say we've got a cross-section. Let's do this. Drag, you double the speed. What happens to the drag when you double the speed? Well, if f of d is equal to 1/2 rho v squared coefficient of drag times the cross-sectional area. All right, we're leaving this, and let's say when v is equal to 10 miles an hour, let's say when v is equal to 10 miles an hour, then the force of drag is, let's say 50 newtons. 50 newtons. But look what happens now when we let v be 20 miles an hour. Look what happens. Then the force of drag is equal to 1/2 rho, which is already a number, rho, and we'll say, and now we've got 20 squared times c. This is still the same. This is still the same. Look at the difference between 10 squared is 100 and 20 squared is 400. Oh my gosh. So by doubling the speed, the drag goes up 4 times because the drag is squared. This is why when you go really fast in your car, you get crappy gas mileage, because the drag force goes up like 60%, 50%. Just the difference between going 55 miles, 60 miles an hour squared and 70 miles an hour squared. Let's look at the difference. 60 squared is equal to 3,600, and this is equal to 4,900. So you take 4,900 divided by 3,600. It's 1.36. Goes up 36%. Almost half again. That's what happens to your thing. So when you, let's go a little bit further. Overcoming drag. Yeah, I don't think I asked about it. If bicycles doubles the speed, all right, we're not going to look at any of this stuff. Skydiving, all right. Terminal velocity. This is your terminal velocity because you've got air resistance, all right. Now, go watch the Felix Baumgartner Stratus thing. In other words, I think, let's watch this real quick. Cannonball, your maximum speed is going to be about 200 miles per hour, arms and legs stretched out about 120 miles per hour. That'll be your terminal velocity, because eventually the force on the drag force, is going to equal the gravitational force. So when you set these two things equal to each other, and then that's where that coefficient, this becomes different. However, go watch the Felix Baumgartner video, all right, and you'll see that he goes way past 200 miles an hour because he's falling above the atmosphere. He's starting out above the atmosphere. All right, I'm going to stop here. I'm getting excited. I love this stuff, in case you couldn't tell.